A very good morning to one and all. So in this class, actually, we'll be discussing about two concepts. So one is your activation function. Why do we require activation function? So in that particular concept, we have two things. One is your sigmoid activation function and ReLU activation function. Okay. So ReLU activation function is not there in the syllabus, but we'll be trying to understand what is exactly ReLU activation function, what is the importance of using ReLU activation function. So quickly, can somebody tell me what is actually an activation function is? How do you define activation function? So can anybody just let me know what is activation function? You have a sample neural network like this. Okay, let's consider. So this is f11, f12, this is f21, and you have some output. Okay, so here in this output, okay, we'll be applying this function called f with respect to the summation of inputs. Two inputs I am subjecting. Let us say this is x1 input and this is x2 input. Okay, two inputs have been subjected here. So I have summation comma f comma to 1. See, this function which I am applying on all these inputs, this I'll be calling it as activation function. Activation function. Okay, so why do we require activation function? So let's assume it produces some yi cap, so that there is a loss with respect to yi cap, so that yi cap is not equal to yi. Okay, so I'll be applying one function for all my inputs and generating my output. So this particular function, I'll be calling it as activation function. Now in this activation function, I have two types. One is your sigmoid activation function. Second is your ReLU activation function. See, there are many activation functions which I can tell. Here in this case, I have taken sigmoid activation function and will be discussing precisely about sigmoid activation function. See, now, if we want to confine our discussion, let's consider our sigmoid activation function. Okay, sigmoid activation function. Activation function. Okay, let's imagine. See, we'll consider one graph here. Okay, so in this graph, okay, we'll just draw a graph here. In this graph, so I'll consider a curve here. Okay, so I'll be drawing a curve here. So the curve somewhat it similar looks like this. Okay, let's consider something. Okay, it's look like this. So it starts, the value starts from 0. Here the maximum value is 1. Okay, let's imagine I have a point 0.5. Okay, so this is 1 point. At 1 I have this point. So this is my maximum point. So how do you calculate for sigmoid? I have a formula for in logistic regression. We'll be studying what is actually a logistic regression. So where sigmoid function is actually being applied. Let's imagine as of now your yi. So this is my weights. Okay, this is my weights. This is my loss. Okay. So considering this, okay, your sigmoid function always varies between 0 and 1. So 1 is your maximum value. Considering this particular curve, so if it is above 0.5, if the point exists anywhere here, so it will be considered as 1. If the point exists below your 0.5, so below this point, it will be considered as 0. Okay, so your y is calculated, that is y is equal to summation of I is equal to 1 to n my weights wi into I. Okay, wi plus some bias I. I'll be coming back and letting you know. Okay, I'll let you know. See, formula to calculate your sigmoid function is 1 divided by 1 plus e power minus y. Let's see how it happens. Okay, since we are not worried about this particular derivation, this is the derived formula of your sigmoid function. Okay. So now here to find, we need to find this particular y. Y is my activation function. Y is my activation function. So what is the formula of y? Formula of y, here I am having formula of y. Y is equal to summation of I is equal to 1 to n wi xi plus bi. Okay, some bias. So that is your activation of y. After getting the value of y, you will apply it to sigmoid function here. Did you understand? Okay, so what is your minimum value in sigmoid function? What is my minimum values in sigma? 0 is my minimum value, 1 is my maximum value. In between your minimum and maximum, you will put up a threshold value, let's say 0.5. If the value is greater than 0.5, it goes to 1. If it is less than 0.5, it goes to the category of 0. Okay. This is what a sigmoid activation function does. Okay, so we'll come back to the discussion again. Yesterday we discussed what is gradient descent. Okay, so your gradient descent curve looks like this. So if this is the curve, okay, if this is the curve, let's imagine, so this is your slope. Okay, this particular, is it a positive slope or a negative slope?
Negative slope.
Negative slope. So this is your negative slope. So this is your positive slope. This is your point where exactly this actually the loss is 0. Loss is equal to 0. Okay. This is the point where we have to reach. Okay. So what is the weight? To calculate the weight, we have with respect to back propagation, that is W nu is equal to W old minus neta times of derivative of loss divided by derivative of weight. Okay, so the new weight is calculated using this formula. Now we need to know, see, come back, we need to know what exactly happens with respect to this. Yesterday we discussed chain rule. Okay, yesterday we discussed chain rule, but during that particular chain rule, we consider this particular derivative of L with respect to derivative of W, right? So here in this today's session, we'll be discussing about only about activation function. See, in activation function, let's imagine I'll be considering only one single neural network. Okay, I'll be considering one network, that is I have one neuron. For this I'm having some inputs, let us say about 3 inputs. So this is my x1, this is x2, this is x3. So this is my function Fij. Okay, so I have my weights for this. So weights I'm having w1, w2, w3. Let's imagine. Okay, so I have an output for this particular thing. So let's say after applying, so this is the sum of all inputs. Let us say the sum of all these weights, I'll call it as Z, of sum of all inputs. So here I'm having Z comma Fij. So the output will be your Fij of Z. Correct? Is it correct? I'm applying this function to all the sum of the inputs. What is that? All my inputs. So I'm applying this particular function to this Z. It becomes, the output will be f of ij of Z. Okay. So if you consider only W, single W, if I consider the capital W, it will be somewhat like matrix of W1, W2, W3, W4. Is it correct? If I consider X here, so it will be somewhat, it will be consisting of X1, X2, X3, X4. Okay. So here our main intention is, if we consider this derivative of loss with respect to W, I need to, in sigmoid function, we will be concentrating on the sigmoid is represented as sigmoid, this symbol. Sigmoid of Z is equal to e power Z divided by 1 plus e power Z. So this is the formula, or it can be written as 1 divided by 1 plus e power minus Z. Okay, any formula, either this or this. Okay, it's look like same. So I just want to go ahead. So how this happens? Let's consider this. If sigmoid of Z is equal to 1 divided by 1 plus e power minus Z. Please remember this formula. It's very important. Okay, you must remember this formula. Now I am finding the derivative of this particular sigmoid. In previous case, we took this Z, we applied sigmoid function to this. What is the formula? E power Z divided by 1 plus e power Z. Now I want to find the derivative of this particular sigmoid function only. So if I want to find the derivative, could you please remember in your when we comes to differentiation, what is the derivative formula to find? So derivative of sigmoid. So derivative of sigmoid with respect to derivative of Z is equal to, can anybody tell me what is the formula? It will be, what is you just let me know, what is derivative of A with respect to derivative of Z? How do we find the derivative? It is A into 1 minus A. Could you remember this? Yes?
Yes.
So derivative of A is derivative, it is A into 1 minus A. Similarly, I am finding the derivative of sigma here. What it will be? Sigma of Z into 1 minus sigma of Z. Correct? So this is my general notation. If I apply the same formula here, I'll be getting sigmoid of Z into 1 minus sigmoid of Z. That is sigmoid of Z will be, can be used, let's say can be used, so this is what the formula is. It can be used in forward propagation also, and also to find the derivatives. So to find the derivatives during back propagation. Okay, please remember this. Where do we use this sigmoid function? It's very important. We use sigmoid function during forward propagation and also finding the derivative during your back propagation. If I want to find the derivative of anything, we'll be using chain rule. Okay, so to find this particular derivative, the internal function which is being applied to find this particular derivative is my sigmoid function. Is there any doubts now? Please unmute yourself and just confirm me how have you understood why do we require sigmoid function? What is activation function? We have types of activation functions. One of the type of activation function is sigmoid function. Why do we require sigmoid function? We require sigmoid function to find the derivative. It can be used in forward propagation also, and to find the derivative using backward propagation also. Is there any doubts?
No, sir.
Okay. Now, see, probably few students might ask how this derivation came. Okay, because we'll not be discussing in detail how do we derive this. For that particular derivation, you can just go through. I'll be showing one. Let's say I'll go to one particular blog. You can just type here. Okay, I'll be typing. Uh, Roni, you can just Roni dot rest blog Sigmoid. I don't know whether we can get it or not. Okay, I think it's not available. Sigmoid function. Yes, yes. Are you able to see this?
Yes, sir.
Yes, sir.
Okay, see, this is the beautiful blog which in which you can go and search with the sigmoid function. See, sigmoid function, it looks like this. Okay, there's a curve which is being present. So, what is my function? That is the formula for this curve is 1 divided by 1 plus e power minus z. So, how does this particular derivation has been got? Okay, you can go through the website here. He has given you the particular derivation and the steps for derivation. So those who are interested to know more about derivation, they can go through this particular blog. Okay, I'll be sharing the link with this. Okay, see, if you are see, this is very much important. This is very much important. See, observe here. This is my sigmoid. See the blue color curve. Okay, this is your sigmoid. Okay, so this is your derivative. Okay, how do I find after applying your sigmoid function? That is your derivative of sigmoid with respect to derivative of z. Okay, after applying this particular formula, derivative of z into 1 minus derivative of z. Okay, after applying this formula, we'll be getting this particular curve. If you observe this curve, this is the derivative curve. So, what is the difference that you can find with respect to the existing curve, sigmoid curve, and this particular derived curve? Can anybody let me know what is the difference which we can find it here?
Point 6.
0.6. Can you just brief what is the difference between this and this curve after applying derivative to this particular sigmoid?
Threshold.
Yes, my threshold value is been decreasing or increasing. Is my threshold value is decreasing or increasing?
Increasing.
Huh?
Moving upwards.
My threshold value is decreasing, right? So it was around 0.5 here. So it was 0.5. Now it has been nearly to 0.2. So it has been decreasing here. So after finding your derivative of sigmoid function, your curve is coming down. So at one point, when it reaches 0, it means that there is no loss. Loss is equal to 0. Okay. So it means that your yi cap is equal to yi. Okay, this is what you can come to a conclusion. Okay, so now let's go back. Let's go back here. So we have a concept called, we also have another function. Okay, apart from sigmoid function, we have functions like ReLU. Okay, ReLU activation function, and also you have tan H activation function. For example, tan H activation function is having the formula A is equal to tan H of Z, that is equal to e power z minus e power minus z divided by e power z plus e power minus z. So this is the tan h value formula. Okay, where please note that you somebody can, I'll be just informing, somebody can give a talk on ReLU activation function, and also we have another activation called as leaky ReLU. Okay, leaky ReLU. See, these are the two activation functions. Right now, these are very much used here. Okay. Now Let's go with respect to our discussion. Next, we have a concept of vanishing gradient descent. Vanishing gradient descent. Okay. So in vanishing gradient descent, you need to know, we'll be learning what is actually, we know already what is actually gradient descent is, what is vanishing gradient descent problem, where exactly, what is this particular problem is associated with. We'll be learning what is stochastic gradient descent. Okay, that's it. Okay, we'll be learning what is gradient descent, what is stochastic gradient descent, what is the problem. By considering this problem, we'll be knowing these two kinds of topic. Let's imagine now, let's imagine, we'll come back. So if we consider this particular neural network, okay, let's go to this, I can consider one neural network. Okay. Mm, okay, let me draw a neural network, one more neural network. Okay, okay, I have a neural network like this. Okay, so let me consider, or I can draw it directly, your values. Let us say my derivative value, I want to find the derivative of loss with respect to derivative of W11. Okay, so derivative of loss, I'll be considering derivative of loss with respect to derivative of out O31 into derivative of O31 divided by, this is O31 divided by derivative of O21, derivative of O21 divided by derivative of O11, derivative of O11 divided by derivative of, this will be W11 power 1. Okay, W11 power 1 plus derivative of O31 divided by derivative of 022. Okay, O22 into derivative of O22 derivative of O11. Okay, O2 O11 and derivative of O11 divided by derivative of W11 power 1. Okay. Uh, so how we took this, considering there are considering a particular neural network with about let's say I have about three, here I have two, here I have one. Okay, considering, let's say this particular network I am considering. So what is the, so this is, I am having x1, x2, x3. So these are my inputs. Considering this, okay, what is my weight with respect to this? Can anybody just tell me the weight here quickly? Let me draw here again. Okay, I'll be writing 1, 2, 3, 4. Here I'm having 1, 2, 3. Here I'm having 1, 2. Here I'm having 1, 2. Are you people able to understand this? So here I'm having this. It will be connected to this. It will be connected to this. So I want to calculate. So this is my, let's say F11. This is my F21. This is my F31. Okay, this is my F41. Okay, so what is my weight here? What is my weight here? Can anybody just tell me quickly? W of
W12.
W
1
one
Power 1.
power
power
2.
2.
2. Okay, here it is W of
Uh,
1
1
power
1 power 3.
1 power 3. So here if it is input, what is the weight here which I am giving? W
1 power 1.
1
1
power
1
1.
power 1.
Okay, so now if I want to calculate, let's imagine, so we don't have this particular network, still will not consider this whole network. Let's say I'm having, this is my output. Okay, this is my output. So here it will be connected to this, here it will be connected to this. Okay, I want to find this particular thing, W11 power 1. So what is the loss when I compare with this? Here it is having, this is O1, this is F21, this is F31. So the output of this will be, O31, this is O21, this is O11. Am I correct? Yes?
Yes, sir.
Okay, now I want to find this particular thing. So if I want to find this particular thing, I'll be considering from derivative of from here. So derivative of L with respect to O31 is O31 divided by O21. Chain rule I have applied here. So this is for this will be the derivative. If I take this particular root, so I'll be summation with this particular thing. Now individually I want to find the particular derivative. Let's imagine, okay, I have found out the derivative of all these things, assuming that I have found the derivative of, let's say I have uh, okay, let's consider summation of O31 divided by derivative of O21. Here I having derivative of O21 and derivative of O11, and I have derivative of O11 and derivative of W11 power 1. I'm just taking this value. Okay, I'm just taking this particular value. Let's imagine, let's imagine the after finding the derivative, the value which I have got is 0.2. For this value I have got is 0.1. For this value I have got is 0.05. Okay, if you multiply all these things, since it is going to multiply all these things approximately, see 0.2 is less than 1, 0.1 is less than 1, 0.05 it is less than 1. What is my value? Can anybody let me know quickly what is the value if you multiply all these three things?
.01.
0.0010 or anything. This is approximately, it is, can I write it as 10 power minus 3? So it is still again, it is less than 1. Okay. So you must remember that, please remember that. See, in sigmoid function, after applying the derivative, your sigmoid function actually lies between, the value of sigmoid function lies between 0 and 1. Okay. So the actual transfer value, what is the transfer value of sigmoid? Transfer value of sigmoid varies between your, that is transfer value means after finding the derivative of sigmoid. Your derivative of sigmoid with respect to derivative of weight or z, which you can call it as, it varies between 0 and 0.25. Please remember this. I want to stress once again, your sigmoid value varies between 0 and 1, the whole value. Okay. Your output of sigmoid function, it varies between the value between 0 and 1. The derivative of sigma with respect to z means here the inputs, the summation of inputs, always varies between 0 to 0.25. This is what the conclusion I want to make. Okay. So any example, if we find the example, considering this here, what we find out, we found that it is 0.0010. Okay. So if I apply to this formula, what is the formula which I am having? That is weight W11 nu is equal to W11 power 1 W11 power 1 nu is equal to W11 power 1, that is old, minus neta times of derivative of L divided by derivative of W11 power 1 of old. If I apply this formula now, see, come back, what is the answer that we have got for this? That is 0.0010. I'll apply to this formula. What is the old value? Old value, let us say I had about, assume that it is about 2.5 minus, let us say my learning rate is 1 into what is the value? 0.0010. 0.0010. Can anybody quickly let me know what is the value of this? It is, what is the value?
2.499.
4996. 499.
2.499.
49.
It is less than this. Okay, old value, your new value is updated now. So W new is 2.49, which is less than this. Okay, so this is how your new value is being updated after applying your sigmoid function. Now you need to know. Let me draw your gradient descent curve. Okay, your gradient descent curve looks like this. If it is my this point, it is your negative curve. This is your if it is this point, it is a positive curve. Positive curve. This point, as you can see here, we call this point as global minima. Global minima. So in next class, I'll be discussing about what is actually a global minima, local minima, okay, global maxima and local maxima, okay. I just wanted to bring it to your awareness that what is the difference between your gradient descent, okay, stochastic gradient descent, okay. So now you please write down this, please remember this, whatever we discussed now. If I consider this derivative of L with respect to derivative of W for let us say, I'll create like this. If it is for n data points, n data points, n data points, it is gradient descent. Gradient descent. Okay. gradient descent. If I consider this particular derivative of L with respect to W for only single one data point, I will be call it as stochastic gradient descent. So let's say another situation, I'll be calculating this derivative of loss with respect to W for k data points, where where k is less than n. Let's say 100 is my data points. If I calculate the derivative of for all the 100 points, it is gradient descent. If I consider only one data point and calculate the derivative, it is stochastic gradient descent point. If I calculate for, let's say, for about 50 data points, which is actually less than 100, I will be telling it as mini batch stochastic gradient descent. Mini batch stochastic gradient descent. Did you understand the difference between gradient descent point, stochastic gradient descent, mini batch stochastic gradient descent? Did you understand this?
Yes, sir. Yes, sir.
So what is this? So gradient descent is finding the slope. That's it. Okay, we are finding the derivative, finding the slope. So if I want to find the slope of all the data points, it is gradient descent. If I am finding only for one data point, it is stochastic gradient descent. If I want to find the derivative for k data points where k is less than n, I will be calling it as mini batch stochastic gradient descent. Okay, is there any doubts with respect to these three things? Because after you understand this particular three things, I can go further. Can we go further?
Yes, sir. Yes, sir.
Okay, see, let's consider now. I'll be writing the formula for this now. Okay, I'll be writing the formula. That is loss function, loss value is equal to summation of I is equal to 1 to n, I is equal to 1 to n, y minus yi cap whole square. This, okay, this is my mini batch formula for mini batch SGD. Okay, now let's say this formula I will be writing it as summation of I is equal to 1 to n. Okay, so yi minus yi cap. Okay, so this is 1 to k, sorry, this is 1 to k, where k is less than n. This is my mini batch. If I take from I is equal to 1 to n, yi minus yi cap whole square, this is my gradient descent. So for stochastic gradient descent, it is not, I'll just remove this particular thing. So I'll be writing it as yi minus yi cap whole square. This is my stochastic gradient descent. Are you understanding?
Yes, sir.
Are you understanding?
Yes, sir.
Yes, sir.
Okay, okay. So, okay. So in this today's class, okay, in this today's session, we have discussed. Let's have a quick revise. See, 5 minutes. I'll be discussing the whole juice of this concept. Please remember. See, today we started with the discussion of actually activation function. So what is activation function? Let's imagine we have a neural network. So for all the neural networks, I have all the data points which will be coming here. I will be applying one function to all the inputs here, that is summation of all the inputs, which I will be calling it as Z here. Okay, Z is my all my inputs. So I'll be applying one particular function called as activation function. See, in activation function, I told you that there are many types of activation function. One is your sigmoid function. Second is your ReLU activation function. We have the third activation function as tan H activation function, and also we have leaky ReLU. Leaky ReLU. Okay, these are all the types of activation functions we have, but we are not going to discuss in detail about three activation functions, that is ReLU, tan H, or leaky. As per our syllabus, we are having sigmoid activation function. So what is sigmoid activation function? Sigmoid activation function, let us consider, if this is my graph, so sigmoid activation function, if I apply, let's say this is my curve here, 0 is my minimum value, 1 is my maximum value. I'll put a threshold value, let's say about 0.5. If my data point lies below my threshold value, it will be considered as 0. If it lies above the threshold value, it will be considered as 1. Okay, so next, what is the formula for sigmoid function? I'm having 1 divided by 1 plus e power minus z. So the formula, how the derivation came, I showed you in this particular blog. You have this blog, please go to this blog. Okay, today after this class, please go to this blog, that is Roni space Restrepo. Okay, in this blog he has clearly explained you the derivation part, how exactly your sigmoid function derivation came. Okay, so this is how your curve looks like. So from this curve, we came to know that this is the normal sigmoid curve. After applying the derivative, so my curve got decreased. It means that my threshold value, the loss is being decreasing. It is nearby to 0. If it is equal to 0, it means that there is no loss, and your yi cap is equal to yi. So after this, we came and we just discussed considering your gradient descent curve. So gradient descent curve, we have positive and negative slope. So at the bottom, we have a point that we call it as where loss is equal to 0, or it is axis parallel. So the formula is W nu is equal to W old minus theta times of derivative of L with respect to W. What is my main intention here? I want to find the sigmoid function of this particular derivative. So for this, I'll be considering the sigma of z, where z is all the inputs, the formula we wrote. Next, also applying the derivative to your sigma. So sigmoid function, we have that particular formula. When I apply the derivative to your sigma, I have sigma of z into 1 minus sigma of z. How did it came? Your derivative formula, derivative of a can be written as a into 1 minus a. So your derivative of z, sigmoid of z, is always used in two things. One is during forward propagation, and second is using to find the derivative during the backward propagation. So after this, we also have tan function. I wrote the formula for tan function. Okay, and then we studied about what is vanishing gradient descent problem. See, in vanishing gradient descent problem, what is the difference with respect to gradient descent in vanishing gradient descent? So I considered three situations. So if I consider this particular thing, we just took one particular instance. We wrote the values, what is the possible values here. We multiplied, we calculated this which is less than, the final answer is less than 1. And then what is my sigmoid value is actually lies between your 0 and 1. The derivative of sigma always lies between 0 and 0.25. Now, after applying this formula, we came to this conclusion. So what is the difference between your gradient descent, stochastic gradient descent, and also your mini batch stochastic gradient descent? If I consider the derivative of this particular loss with respect to W, if I'm finding the derivative of all the data points, it is gradient descent. It means we are finding the slope for all the data points. If I am finding the slope only for one single data point, it is called as stochastic gradient descent. If I am finding the derivative for only k points, where k is less than n, I'll be calling it as mini batch stochastic gradient descent. So the formula which is associated with this is I is equal to 1 to k, where k is less than n. That is mini batch. So these are all the things remain same. Y minus yi cap whole square remains same. Only things is these things changes. So for this I is equal to 1 to k. So this is I is equal to 1 to n. So for this, since it is single data point, I don't have anything. So it is simply 1 into yi minus yi cap whole square, which is stochastic gradient descent point. Okay, so this is how in textbook, see, if you observe the textbook, he has given half. Okay, 1 by 2 into summation of I is equal to 1 to n, I is equal to 1 to n into yi minus yi cap whole square. It is similar, it is equal to this. So there is no change in this. So please go through the textbook once. He has given a beautiful explanation. Okay, if you okay, and he has also given like this. It is TD, okay, TD and OD. TD means what? It is training data. OD means it is output data. Okay, so the notations is slightly different when we have explanation here in this class, and also for the explanation what he has given in the textbook. So here I would like to stop today's discussion. Okay, so we have just revised all the concept. If you have any doubts with respect to today's concept, you can just let me know. Okay.